actual concept of angular momentum? Well, as you know, linear momentum is mathematically equal to the multiplication of mass and velocity. Therefore, any moving object has linear momentum. Similarly, the angular momentum is the product of angular velocity and the mass moment of inertia. The only difference between these two vector quantities is that angular momentum deals with rotation and spinning objects. As we just mentioned, angular momentum equals I multiplied by omega. But the moment of inertia might seem a little complicated at the first glance. It is somehow analogous to mass, an object's resistance to motion. For instance, it is quite difficult to displace massive objects, and it requires a lot of energy to alter their situation. According to Newton's second law, an object's acceleration is inversely proportional to its mass. This statement implies that with a constant magnitude of force, things get accelerated more easily when they are lighter. The same is true for the mass moment of inertia. It resists rotation. Bodies with greater moment of inertia require greater magnitude of torque to generate rotation. A spinning object with a constant value of angular momentum will rotate faster if the moment of inertia is small. To put it another way, I and omega are inversely proportional. The moment of inertia depends on several parameters. It depends not only on the object's mass but also the distribution of the mass in relation to the axis of rotation. This relation means that the mass moment of inertia is higher for objects where the mass is distributed a long way away from the axis of rotation. Imagine an ice skater is rotating around herself. If she pulls her arms in, her moment of inertia decreases and she can rotate faster with the same effort. The mass moment of inertia has distinct values for different geometries. You can simply find most of them in engineering handbooks. As an example, imagine a point object rotating about a particular axis. We know that the mass moment of inertia in this case is equal to, which can be easily proven by noticing that angular momentum is basically defined as, where p is the linear momentum. Besides, the linear velocity of this concentrated mass equals. By substituting these relations, we come to this final formula. Now let us see when the angular momentum is conserved. Generally, the torque exerted to a system can be defined as the rate of the change of angular momentum. When no external force is applied, this rate will equal 0, which means the total magnitude of angular momentum is conserved. In other words, the angular momentum will remain constant. We can see the conservation of angular momentum everywhere in nature. All the planets in our solar system keep rotating about their own axis owing to this conservation. Another instance is the self-rotate or spin of electrons in an atom. Electrons possess angular momentum, which is conserved in this case. The angular momentum of the ice skater is also approximately constant if we neglect the insignificant effects of friction and air drag. As we mentioned earlier, when the angular momentum is constant, a decrease in the value of mass moment of inertia will result in an increase in angular velocity. Hope you have enjoyed watching this video about angular momentum. Feel free to ask us your question, and as always, don't forget to subscribe.